So I hope at this point we've got a bit of a sense about this, this issue we have notationally where there's a bit of an embarrassment going on here because I'm using H as a monomorphism and also as a function. We're going to turn this embarrassment into a feature by using category theory. So the idea is that we will try to annotate what kinds of arrows we're talking about. Are we talking about function arrows? Are we talking about monoid arrows? What is the world that we're dealing with? And ultimately, what we're doing when we're doing category theory is we're saying, here is a collection of arrows that work together in some sensible way. And in order to do that, you always need an identity arrow, like this, and a composition, like this. And those are the two things that sort of make the arrows connect together in the category. So with ordinary sets and functions, the identity function and function composition works. Here we've got the identity monoid homomorphism and the composition of monoid homomorphisms, and they get connected as well for trivial reasons. So let's talk about what a category is more formally. Sorry.
So, also a quick question about math review.
Yes.
You said it's a monoid homomorphism, right?
Yes.
But how do you enforce a monoid equation on the...
You don't.
You don't?
No.
So it's not really a monoid.
Well, if B is a monoid, then it's a monoid homomorphism.
So it's only if.
Yeah.
Yeah.
So, and indeed, that's always the case with monoid homomorphisms. So, if we look at this here, we're saying if this is a monoid and this is a monoid, then this is a homomorphism.
Right.
And in the same way, if
Right, okay. Yeah.
the B is a monoid, then indeed it is a monoid homomorphism.
Great, thank you.
All right. So, what is a category? So, there are many ways of explaining what a category is. I'm going to try not to lie too much, but there will be a few lies. A category is, so we're going to have a set of objects. This thing which we'll call R. We're going to need identities, and we're going to need compositions. Where? Okay, so this is the data, and then I'm going to put some conditions on what this data needs to be. It's always been the case that obj is a set. So just as I monoids wrote n is a set, I'm writing here obj is a set. So it's just a set of things, I'm calling it obj. This is the set of objects. For your intuition, in sets and functions, this will be the set of all sets. Or in monoids, the set of all monoids. And if x and y are in obj, since we know that obj is a set, this really is set inclusion, then I want to say that hom xy, that needs to be a set. Okay. So this whole thing is a bit weird because it takes in, it takes in two elements of this thing, and it says that this is a set. So when I give you two elements of the objects, hom is a self-set. And the intuition is that this is going to be the set of all functions from x to y. So in the back of your mind, you might be imagining this is like the same thing as this. So here we want to think like, of just a set of all sets, we can think of it like some universe with everything. And if x and y are in that universe, then this is the set of all functions, the total functions are connected together. Okay? We also need a few more things. We need to ensure that for every X in POM. So for every object in this world, we want to make sure that there is a corresponding morphism in. Okay, so here think, remember the intuition is this is functions from x to y. So this is like functions from x to x. So this is just saying for every object, there exists an identity function on that object, something that makes it go back to itself. The next one I need is, so if f is in POM from x to y, and g is in POM from y to z, then g compose f is in POM x to z. So what you should be thinking here is, I'm giving you a piece of data with 4 things in it. Obj, POM, id, and com. And here, I'm telling you where these things come from, right? Here I'm saying, obj is a set. Here I'm saying, POM x, y is a set, whether x and y are objects. Here I'm telling you, identities come from objects. So every object gives rise to an identity. And here I'm telling you, compositions come from the fact that whenever you've got 2 arrows, you can compose them together. So these are the sort of typing rules that tell you what these 4 things do in some sense. But this all needs to be subject to well-formedness conditions. So I can't just stick. There's a bit more to do with the identities than we would expect. In particular, we expect the identity to be a bit like the identity function. It shouldn't change stuff. So I should write that down as well. So for any f in POM x, y, we have that f dot id on x is equal to f is equal to id x and y after f. Okay. So this is saying that the identity really doesn't do anything when you compose it. And in some sense, this is the first time that we've linked together composition and identity together. I told you how they behave when they interact. What I haven't done is told you how composition interacts with itself. So, f is in POM wx, g is in POM xy, and h is in POM y and z. Then h dot g dot f equals h dot g dot f, no matter how I put my parentheses. So this is the associativity. Okay. Now, notationally, what did I mention? I'm going to get a bit fed up of writing POM and obj everywhere. And furthermore, I will want to be telling you which category I'm dealing with when I'm dealing with different categories. So here, obj, POM, id, and dot don't talk about the category C that they're in. It's kind of ambient and obvious. But I want to have notation that allows me to work with different categories at the same time. So what I'm going to say is, instead of writing x is in obj for some category C, I'm going to write x colon C. That means x is an object in the category C whose set is obj blah 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 blah, right? And instead of saying f is in POM x, y, I'm going to be a bit bored of writing that. I'm going to write f is from x to y in C. Okay? And if I'm really lazy, I might not even write the C. So I've kept that up here. hopefully you can see that this output board to the monoid part corresponds fairly closely to what's going on down here. So we've got the epsilons are the identities, and the plusal is the dots that we have down here. Yeah. So hopefully you can believe me that monoids form a category. The set of all monoids forms a category. Hopefully you will believe me that sets and functions also form a category. Do I have any questions about this? Yeah.
What is it?
What's a set? I don't know.
That's someone
Yeah.
all the time, right?
Let me ask a different question to you. How picky are you being?
That's why I'm asking.
Yeah.
How big you want to
Yeah. So we have what we call size issues right now, and they're quite bad. And I'm hoping to brush them under the carpet. So for those of you who know about these things, size issues come about with this thing. This starts to look like Russell's paradox, which tells you that when you start saying things like the sets of all sets, you should start getting a bit worried with yourself, because what about the set of all sets that don't contain themselves, and then suddenly the world goes bang because it's in itself, yes or no, nobody knows, right? So there are two ways out of this quandary. Whenever I said a set, it didn't mean a set, it meant a collection. And a collection is either a set or a class, and you can't construct classes of all things in the normal ways, so this is the picky answer. And then we distinguish between what we call large categories and small categories. And small categories are when everything truly is a set, and large categories is when either the opt or the hom sets are classes, and then a locally small category is when the hom is a set and not a class. That's one answer. And you're nodding, so hopefully that makes sense to you. If it doesn't make sense to you, just put up with my noise. The slightly more, the different answer to that question without going through sets and classes is we could talk about universal hierarchies instead. So we have the set, all sets smaller than something, and then we can increase the hierarchy by having slightly larger sets that include all those things beneath them, and so on and so on. And you can do a stratified category theory using universal hierarchies instead. But again, I'm going to brush this under the carpet and we didn't have this conversation. But okay, any other questions? Yeah.
That's the plus the like relevance. It's not a good idea of encouragement, right?
Yeah.
And then you went on that whole program function that we wanted.
Yes.
That was idea, right?
Yeah.
And then start to write all this.
All the stuff wants to start.
Yes. And I can see you started like a small one and just function next to the graph, and then you expand it to the whole, the noise, and then whole. And I can see like you're dealing with the same things, but just like the larger scale, as you are generalized.
Yes.
What's the point of that? You can't do.
Yeah. Good, thank you. Yeah. So this is definitely my weakness when lecturing, is that I'll get carried away and forget the work I'm doing. And so
The reason I'm asking because I can see the same thing, nothing's changed. The only thing is the annotation is just like that's just on my set, and
Yes.
we're talking about object and categories and
Yes.
one more.
yeah. So
It's the same. So
it's all the same so far. Why the abstraction, right?
yes.
Good. I'm actually giving us some tools in order to tackle a harder problem in a minute. We talked about MapReduce, and it seemed like we were quite satisfied with MapReduce. I'm about to throw some build programs at you that don't fit the pattern of MapReduce, and we're going to be very sad about that because it thought we had something nice. And then what I'll do is I'll say, drat. If only we had some theory that allowed us to understand why MapReduce was nice, can we use that same theory to come up with something we're going to get? So I'm kind of giving us the toolbox that we need so that you can begin to understand why MapReduce was actually good, so that when we hit it with something that it can't cope with, we'll have what we need to continue with that story. But thank you so much, because I think losing the plot is the easiest thing in something as abstract as this, and it's really good to ground back. So if you do forget what we're doing and why we're doing it, this is the perfect question to ask. Slow me down and ask me, because it's easy for me to read now. Yeah, thanks. Anybody else? Yeah.
Yeah, about the notation.
Yeah.
Right? Because it's quite mathematical, but let's say you always have these brackets. Let's say you have a nominator and a denominator, and you say that, for example, like in the second line, if x and y, I'm on the second line.
This one?
Yeah, if x and y is an element of or is an element of object, then you have this morphism.
Yes.
And wondering whether that's, let's say, a general notation, let's say in Imperialism, or because in mathematics you just write one line and
Yeah.
say, given provided the assumptions is
Something like this.
yeah, exactly. So
Right?
yeah,
Yeah. So this notation goes back to like Gibson proof trees. It's quite old. So it's, I don't know, about 150 to 200 years old, is that right? And it's basically a replacement for this kind of notation. It just says if the stuff above the line is true, then the stuff below the line is true. So it's basically an implication. And it's, if you look at like logical constructions of logic itself, you'll see this kind of notation everywhere. So it's just a convenient thing to write on the whiteboard. That means I don't have to write quite so many for all quantifiers and there exist quantifiers, etc., etc. But all I'm saying is, if this is true, then that is true.
it's like I have practically not abstraction but compression.
I'm just compressing the notation. Yeah.
Yeah, and then these angular brackets. So I mean, the mathematics is that would be a vector product. Yeah, exactly.
Yeah.
So
This is not vector product. Think of this as just a ordered tuple of things, and the things don't have to have the same types. So they're just things in that order. I haven't really told you what they are until I start doing this. So this is like, here are 4 things. I've given them 4 different names, and here's what I expect of them.
this category, so it implies that first an object, second you have like this,
Yeah.
thirdly that you have an identity. And
Yeah.
lastly,
Yes. So it's a really great question. There's nothing. So let's talk about monoids first. Here I gave you the definition of monoids in much the same way. I said a monoid is these 3 things and some interaction between them. When we're doing this kind of semi-formal mathematics, we need a way of saying, I've got an idea. It's the interaction of these 3 things or these 4 things. How am I going to write that down? How do I write, here are 4 things and here are their interactions? Well, I just need to say I've got 3 things in this case, 1, 2, 3, in this order, and here's how they interact. Now I could have changed the order of these things, so long as the interactions were the same. That didn't matter. That's not important. The important part is I'm going to give you 3 things, and this is what they do.
It looks like a space, like a vector space, so like a probability space where you have a member, you have let's say a filtration, and you have a way you interact across time. And this is what
You can think of it like that, although this is nowhere near as structured as a vector space.
it's just collection, and you
It's just a collection of
angular brackets that you objects. Yes, it's in
I'm just saying 3 things. So I could have used different notation. I had to use something. I just used this. I could have used round brackets. I could have not used brackets and just written it in English with 3 things in order. It doesn't really matter too much. This part is a notation in detail. Good question, right? Notation's like one of those terrible things. I really despise it when people say, "Oh, it's just syntax." Like, what are you talking about? All we ever do is just syntax. Okay. Any other questions?
Last one, but this very good. Again, second line, you have homomorphism of x and y that are set. They're exactly this guy. So you like the thing is the set. Why does the set come out from the homomorphism and not the non-form?
Good question. It's me being really lazy. I could have written is a set instead. Like here is a set.
So it has nothing to do with information from right to left and all, because there's also languages that interpret from left to right, or precedence. Some languages offer right to left, and others completely confused.
Yeah.
So this is just clarifies like the homomorphisms.
Yeah. So I need a way of telling you that something is a set, and I've decided to do that by writing the thing and then the word set, and that's just saying this is a set or this is a set. And it's just, again, I'm just being a bit lazy, and I'm removing the words is and a, and then hopefully you understand that I'm trying to say this is a set.
We have the notes, but if people want to read up on that stuff,
No, you're getting this fresh off the press right now. I'm afraid that means you're all guinea pigs. Anyone else? Okay. So we've got as far as a category. I've shown you sets and functions. Ah, yes. Now I want to say something important. Hask is a category. Not. Okay? Hask is not a category. So you will read on the internet people having wonderful debates about Haskell being a category, and they're wrong. It's not a category. People treat it like it's a category. It isn't. It's quite easy to prove that it's not a category. So there is a function called seek in Haskell, which in some sense is the most Haskell function of them all. So what does seek do? Seek says, I'm going to take two terms in, x and y, and I'm definitely going to evaluate x, and then I'm going to evaluate y and give you the result of y. Okay? So seek of x, y is equal to y, but with this really weird condition that seek of bottom y is bottom. So for those who don't know, bottom is just another word for undefined. It means your phone spins and gets very hot, and who knows what happens here. It means if you try to evaluate, the system explodes. Okay? And this little conversation is largely for people who are like, do lots of Haskell, and they think, oh, I know some category theory, I know some Haskell. I've heard the words functors, monads, and natural transformations. Clearly, these are all Haskell concepts. Haskell is a category. In fact, I've read Haskell as a category, and surely it is. The answer is, well, let's look at the behavior of seek. So, seek of bottom of unit. What's that? Well, that's bottom. So, what about seek of bottom id of unit? Plug it into your GHCI instances and see what happens. What do you think should happen? So there has to be people in the room. What should happen? It should give you bottom. Why? Did I hear something? No?
Yeah, we just pass the to the bottom, and then it should be the bottom.
Okay, so it seems like bottom.id should be bottom. We use this equation with bottom. Okay, that's one idea. What's an alternative thing that this might happen?
It'll stay going.
Well, it could keep going, yeah. If it keeps going, I'll call that bottom. So the definition of bottom is bottom of bottom. So keep going is exactly bottom. So I'm happy with that. That's the same answer for this. Yeah.
If you have a composition bottom is, that's going to be a function of the type a to a, but as long as it's not applying that function to anything, it might not care if that's undefined and gives you units.
Exactly. So the alternative answer to this is maybe it's unit. Okay? Which one is it? So for Inish, who rightly looked at the equations and saw this, and then went here, that would be the correct answer. Haskell gives you this answer. That tells me that composition and identity don't play nicely in Haskell. That's pretty serious.
What's the rationale for the that?
So the rationale here is what seek does is it evaluates its first argument to head normal form. If you give it bottom, the head normal form of bottom is indeed bottom, but the head normal form of the function is that function. So this is the function, so it's already normalized. So seek of this, no more work to do. Now I have this, because I'm using decimals here. And this is fundamentally to do with the way that Haskell is a lazy language, and this is exactly the only place where you can tell Haskell to, come on, get on, do some work. So this is the function that, like when I said it's fundamentally the most Haskell, it's the function that makes Haskell work, in terms of it's the one that forces evaluation. But it has this property. So there are various ways that you might try to get out of this. Maybe this is a more of a break time conversation, because we don't need to involve the whole room. We could do some like synthetic category theory instead, but then I would ask, are we truly doing Haskell? There's also the fast and loose reasoning is morally correct paper, which tells you that in the absence of bottoms, everything is okay, right? Well, I'm happy with that argument, except that this is a valid Haskell definition, and this is how I can introduce bottoms into the language trivially. So if I'm not allowed to write things like this in my Haskell code, what other things am I not allowed to write? Hang on a minute, aren't we discussing this very topic as we go? There's a bit of recursion going on here. I don't know where to stop, right? So until we can formalize Haskell, we can't formalize Haskell. Bottom, right? So Haskell is not a category. But this is a really pessimistic view of things, right? This is saying, because Haskell is not a category, because of this little thing here, therefore, all of this theory is completely useless. Let's just throw it out the window and not use it at all. That's a bit too strong, right? Actually, I would go even further. Haskell as a language is not well defined, so we don't even know its semantics proper. So our best guess is it's something like system F omega, but that's actually not correct. There are lots of features of Haskell that aren't captured even in that model. So we don't really know what Haskell is any more than we really know what Java is. But I would still claim that the ideas that we're talking about are useful for Java, just as they are in Haskell, and it's okay to study the ideas, but let's not start saying silly things like, in the category Hask, I'm like, well, I just don't even know what you're talking about anymore. Okay, yeah.
Can you explain what bottom means?
So bottom is undefined. It's the, so there are two answers there. Simply put, bottom is bottom. In other words, if you try to evaluate what bottom is, I will say, please value bottom, and then it will tell you what it is. So it will just recurse. So it's equivalent to something like while true. It just makes your CPU hot. It's a bit more nuanced than that because of its type. So bottom has type A for any A you can imagine. So it's also the type of a function, it's also the type of a value, it's also the type of function of function. So it's everything really. It just says, here's a computation that if you try to touch it, will not do this.
This is not anything to do with a lattice here.
Exactly, everything to do with the lattice. So in terms of an informational theory perspective, it is the bottom of a lattice.
Right.
And as you apply, so you know how in lattice, do you know much domain theory? Roughly, domain theory says something like you have an information lattice, the more defined something is, the higher up the lattice is. If you look at the foundations of what a recursive function is, using the work of Scott, you say, first of all, the recursive function is undefined, and then we're going to improve that by saying let's apply the function to that undefined line once, and then again, and then again, and then again, and then at the limits, that's what we think the function is. So for example, if we think about the Fibonacci function, you can say Fibonacci is recursive, but if at the recursive point we put undefined, that's like an approximation of Fibonacci to bad approximation that almost dies straight away. But if we do Fibonacci of Fibonacci at bottom, that will at least do one step of recursion before it dies. And then you can iterate this like n times until you've got your full definition of Fibonacci for any x. It's like, that's where you build the lattice structure, and indeed bottom is the bottom of that because it's the least defined, the most polygon.
How do you live with the fact that it's not a category that talk about functors and method transformations? Do you like add intervals or not like? As in, like, do you treat functions only based on their operational behavior? Like, do you have to throw away the laziness when you use it like this?
Yeah, so that's a really, you're asking me how do I sleep at night?
Yeah, exactly.
So I think I would put it like this. Haskell's a convenient language to do set theory in. It's not actually a language for sets at all. But if you restrict yourself to the things that you know are set-like, it's a jolly good language with nice syntax, with an optimized compiler. If you stray outside of that, now you're in trouble and I can't help you. Yeah, so that's how I see it. Yeah.
Is there some alternative choice of composition and identity that you can use to make it a category that's satisfying?
I think the answer is yes. Matt has suggested something. I haven't looked at the detail, so I don't know the answer to that. But Hask is, in its own right, not a category as we would normally understand it to be. We'd have to transfer value to quite a bit, and that's my thing around.
Yeah.
Yeah.
And in terms of operator precedence in the last line, where you have this, you have binary outcome, the secondary choice of evaluations.
Yeah.
Like one times identity or the other sequence of the bottom of the identity.
Yeah. So the straight answer is it doesn't matter in this example. It's a function that's unevaluated, so it's not being applied to anything right now, so it's already in normal form. But Haskell is a lazy language, so it would normally do outside first. So it would do the outermost regex working its way in. So normally it would do like this outermost thing first. But because this is a function, we don't do anything right now. If I were to do like bottom applies to hint of I would start benefiting this, and now I'm in trouble. But what we're talking about is, again, this is this, so I would evaluate this first. But I didn't talk about this, I talked about just this part here. It's just a function, that's already in normal form, we can't, there's nothing we can do.
Well, we better know before.
Maybe this is what to take on later on. Normal form means something like, when we compute with a function, we keep on computing until it hits a value. A function, it's
in channel,
no, more like when do we stop computing? When do we stop reducing something? When it's in normal form. Okay, any more? Right. So Hask is not a category. Okay. I want to talk about something called functor. So, getting back to that really useful question of why are we doing all of this? I'm trying to equip us with enough information so that we can tackle interesting recurrent schemes. So, a functor is basically a mapping between categories. So it takes in a category and it spits back out a category. We've actually essentially seen a functor already. Suppose I start with a monoid n. And this is a monoid, it's not a set, but we've been talking about the set that belongs to the monoid quite a lot, right? So this is something like this, n. So is there a way to, given this monoid, produce this set? Seems like it's obviously you can, right? And some people use brackets around the monoid to do that. I'm going to write the word U, or the letter U, which stands for underlying. So it's the underlying set of the monoid is this thing. So U of this monoid is equal to this thing here. Okay? Now, you can think of U as a little bit like a function that takes a monoid and produces a set. Well, what is a monoid? A monoid is an object in the category of monoids. And a set is an object in the category of sets. So you can think of this U as some kind of thing that transforms an object in one category into an object in another category. So this U takes in an object in mon and produces something in set. Now, those of you who are picky should complain at me, because I've just drawn an arrow. That's a function. Is this a function? Is mon a function? Sorry, is mon a set? No, mon is a category. So I can't just write this. This is nonsense. But we've seen this before, right? We've seen this problem with monoids, where I said, oh, look, here's a monoid homomorphism, and if I'm a good boy, I'll write something like mon over here. It tells you that this function here isn't an ordinary function, it's a monoid function, monoid homomorphism. And in the same way, I'm going to say, oh, well, here I don't really need an actual function. I need a thing that, given a category, produces a category. So I need to think about the category of categories. So this category of categories is called cat. Okay? So now I'm applying the same logic that I've been applying to everything else. I'm saying that cat itself is also a category. Cat is a category, then I better tell you what the morphisms look like, and I tell you what the identities are, etc. So we're talking about functors are the morphisms in the category of categories. It's a bit confusing. The essential idea is, here's the way of transforming these things, and it has to transform them in a nice way. Okay? What does in a nice way mean? This part is obviously clear. We'll take this monoid and produce this set. What if you gave me a monoid homomorphism? I would quite like to turn that monoid homomorphism into a function. Which function should I choose? Well, this goes back to another thing where there was some awkwardness in the conversation. Here, I said a monoid homomorphism H, blah, 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 is a function H on sets, right? So hopefully there's a correspondence between this H and that H, precisely because this is a mon function, or mon arrow, and this is a set arrow. So if I had a way of transforming mon arrows into set arrows, I'd be jolly happy. Well, I'm telling you here that this thing is a mon to set transformation. So it better not just transform the objects from one place to another, it better also transform the arrows from one place to another. So this is why we would say something like the underlying thing of some homomorphism between epsilon mon to n plus n epsilon n mon. This thing better equal to some function. Which function do I pick? I'll pick the underlying function h when viewed as an m to n function in set. Okay. So hopefully that is kind of a reasonable thing to say. We're just taking function to function. But apart from the name h to h, I'm not really telling you very much about how this works or what it should do or how well behaved it should be. And actually, if you think about it more carefully, let's talk about monoid homomorphisms first, right? So with monoid homomorphisms, I was really careful to say it should preserve the way the identities work. It should preserve the way the compositions work, and that should all behave nicely, right? And why is that? Because a monoid homomorphism takes a monoid to one monoid, preserves the structure. The structure is these three things. That's going to be preserved. The category, what is the structure of the category? It's these four things. So if we're going to transform one category to another, we better preserve the structure of the category as well, just like we did with the monoid. So what should we preserve? Well, we should take objects to objects. Hey, that's the first thing I wrote up there. We took an object, we brought back an object. The second thing we need to do is preserve homomorphisms and preserve arrows. Hey, that's the second thing I did. I wrote an arrow transformation. We should also preserve identities, and I haven't said anything about that yet. So what does it mean to preserve identities? We better write something interesting like that. We should say something like U of the identity monoid homomorphism better be equal to the identity function. So now the identities from one category have been preserved to the other category. Furthermore, I need to be able to say, oh, there are compositions too. I better preserve the structure of the compositions. So I write something like U of, if I have G composed F, this composition here is a monoid homomorphism composition, should be equal to U of G, the underlying function composition U of F over here. Okay, so this is what I would expect. if I'm preserving the structure of a category. And this shouldn't hold just for you. We can generalize and say, if you're talking about any two categories, I should be able to transform to. So let me just write that down here. Are there any questions about this so far? Okay. Yeah, so given some category C, some category D, functor f between C and D in, let's say, at, right? Just to distinguish the arrow, is something where we go, okay, if you give me some object x in C, then f of x better be in D. That says that we have an object-to-object mapping. If we have some f of x to y in C, then we better have f of f is, what are we saying here? It's going to go from f of x to f of y in D. Okay? Now, I think that what I've just written there is a bit confusing because we're used to functions taking in like one thing of one type and it was producing something within that set. But look, this big F is both taking in an object and it's also taking in an arrow. But this is to do with the fact that we're doing like structure preserving stuff. We need to act on everything that's in the category we have proposed. So I could have called it like a functor F is a four tuple of things. The thing that acts on the object, the thing that acts on this, and the thing that, and you can break it all out. But this is the kind of notational convenience that we do to not do. So such that some things have to hold true. So it's always the case that f in x is id fx, or the f in C, and then if f is from x to y is C, and if g is from y to z is C, then f of f to f g then f. Okay. So that's what a functor is. Are there any questions about this?
I might be operating on the wrong scope,
Yeah.
but is categories, comma, functors, comma, something, category. Is this, it looks similar. Is that all categories a category? Does functors go nicely like that?
Absolutely.
Okay.
Very nice observation. So you went, oh, this feels like I'm seeing a pattern here. He's been talking about arrows, and you're anticipating, what if there was an identity functor? A category produce a category. Well, there is such a thing, because if you give me x, then you like x, and if you give me f, then you like f, we can satisfy the rules. And wouldn't it be nice if we propose functors too, right? So suppose we have f, which goes from C to D, and we have G that goes from D to E, then it would be really nice if we could make a functor that goes something like, if you give me an object x in C, then I can make you the functor that goes G composed f of x is indeed a functor from C to D in cat. I should have written in cat to a few more places. And indeed, now that we've got identities and we've got a composition, we can say, ooh, all I need for a category is an identity and a composition and a set of things and blah, 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 blah. Indeed. So cat is a category. Cat is the category of categories, the objects are categories, and the morphisms are functors.
And what one is C to E?
Thank you. Yeah. It's fun. Yeah. All right. Any other questions? Yeah.
These are just covariant functors.
These are just the covariant functors, but all we need to do for the contravariant functors is opt one of the categories and away we go. Yeah. Don't worry if you don't know what it means. Yeah.
Either I'm confused or the identity is the second one meant to be y.
No, it's fx.
Okay.
So if x is an object in C, then by its rule, fx is an object in D.
So the identity is in
So this is the identity of fx, which is in D.
yeah. And the identity of D is it that as well?
Yes, yes. And that's because of what I'm looking at. So given an object x in this category, if x is blah blah blah. So x in this case is fx is.
Yeah.
Anyone else?
In the bottom right, you've applied your functor to an x, so shouldn't the type be an object in E rather than the arrow? Because you've composed two functors.
Yeah. Thank you. Gosh, every part of that was wrong. All right. So yes, we have a category of categories. Yes. Having stressed that Hask is not a category, let's find out what functors it has. I do like how you sleep at that question. So you can think of Haskell as an approximation to sets and functions. It's not quite right, for reasons we've seen, but the data type lists, what does it do? So if I have like an integer, and I make a list of integers, at the type line, this is what we would write. Yeah, I have an integer, or this is a type of list of integers. I don't really like square bracket notation when I have this conversation because it gets in the way and we get confused by the syntax. So I'm going to write the word list instead and pretend that this is how you spell this, okay? So here is a type, and here is also a type. And to first approximation, you can think that a type is a set. This is the set of all the integers. This is the set of all the lists of integers. So what list is, itself, list, is it takes an integer and it produces back the type of all the lists of integers. The list itself says, if you give me a type, I don't know which type it is, any type, I'll produce back to you another type, which is the list of those things. So like, if I give you a list of int, well, I'll give you back, and this is where it gets a bit unfortunate, I could write this, which is clearly true, but a bit trivial, right? But my intention is maybe to write something like this, but now I'm just playing games, because this is just the same thing, okay? But the intuition I'm trying to give you is, if you give me an integer, I'll give you back the list of things. So what list itself is like a set-to-set transformer. It transforms sets of stuff to lists of those things, okay? It is itself a functor. It's a functor in set that, given a set, produces back a set. So it should behave nicely. In particular, list. So given anything, any type, how will I write this? I will do it like, let's do it like this. So given any type or any set, then this will then also be a set. Now, I haven't really described what the set is yet. Hopefully your intuition understands what I'm about to say here. We also need a way of saying, how do we transform the arrows? So remember my definition of functor, I said we need two things. Given an element, we produce something else. That's exactly what I've got there. I also need to say, given a function, I need to produce an arrow in another category. So if you give me f from x to y in set, then list of f better be a list x to list y in z. Okay? That's following what I said down here. Sorry, here. It better be the case that these two laws hold true. Let's talk about that in a minute. What is it exactly that we're describing here? We have a weird two-level system here that we talked about a minute ago. The functor is acting on an object. The functor is also acting on an algorithm, on a function. Haskell doesn't play this kind of notational trick. It's a bit more honest, despite not being a category. So in Haskell, we would say that there is a class of things called a functor, and I'm going to slightly cheat, like f is a function in capital letters, where we have an f mapping function, which oops. Okay, and in particular, we saw earlier on, an instance of this is the mapping function. So this is one of the first things I wrote today. Okay. This says the mapping of lists, which given a function produces a list-to-list transformation, given a function produces a list-to-list transformation. So this list f thing here in Haskell is precisely map for lists. And this list up here is precisely the type constructor for lists. So Haskell splits the type world from the value world. There are two different things. And we see that because this is the value level map, whereas the thing, the square brackets or the word list, that's the type level transformer. They're two different things. Right. Any questions? Yeah.
Yeah, I'm wondering why you're handling on Haskell. Is it because it is a very concise language, or is it because it is implementing, let's say, the theory nicely?
Yeah.
Or is there like a grand scheme of things, a unifying theory across maybe all the languages like C, C++, Python, or
all good programming languages are true and complete, so they're all equal, but some are more equal than others. Haskell plays well with the theory because the ideas that we are coming up with in category theory, like functors, translate very nicely to code that you can write and execute in Haskell. And the translation is quite direct, so you would just write this instead of functor blah blah blah. To do the same in other languages, you have to go through a few more hoops. It's a bit more difficult. So the application is a bit in there.
and why is that?
Syntactically, things just get trickier in other languages.
So Haskell is just a vehicle in which you can implement, let's say, your theoretical considerations in a very forward.
And it's by no means perfect, but it's not bad. So it'll do a better job than JavaScript. It'll do a better job than C++ or Java. It'll do a better job than Scala. But it's not the job I want it to do, but it's the best we've got right now in terms of pragmatism. You can write Haskell code that is within striking distance of C code in terms of its efficiency, but you don't have to pay the price of abstraction. So you can your code can remain quite abstract, still get some good performance, and the dream that I have of wouldn't it be nice if we knew which class of functions were well behaved, what we're doing today is quite well lived out in the Haskell world and quite badly lived out in other languages. Not all other languages, let's talk about other things later, but Haskell is a good language too. Yes?
I think down to the C list, if you the basic thing, if you fill up on that one. So just now you said for the list int in that button. You mean that if you give me something, I will give you a list of something. Yes. I incorporate that. If you give me a type, I will give you a set of the element belong to that.
Yes. So I just want to be a little bit precise. If I give you int, right, this is a type. what does it mean to say, I've got int? Does it mean that you have actually all the integers representable in your CPU? It doesn't quite mean that. It means it's a type annotation. It means if I have a value of this type, I know it belongs to the set. It doesn't mean that I've enumerated all the values. Similarly here, it doesn't mean I've enumerated all the lists. It just means it belongs to the thing that are lists.
So the system will give you a list or a set of elements belong to that list. This is not a foundation. And so for the function, when I be taking up a map, function working with mapping in context. So and then you have to look at the middle f colon x in by y and colon set. They all get something. So that means I will give a list of something belong to x. Then I will give you a list of function mapping to a list of y.
That's correct, yeah.
Then in particle, I believe the map that kind of thing can you elaborate more?
Yes, of course. So let's talk about this again. This is, in some sense, it means the set of all integers, but in some sense it doesn't mean that because I don't say here's an int, and then you think, oh, I've got the set of all the integers. It's just it's type. But if you have something like int to char function, so f has this type. If f defines x, where x is an int, because you've given me a particular element of this set, I will give you back a particular element of that set. So functions are like that with sets, with the notation that they say, if you give me one of these, I will give you back one of these. And in the same way, this is saying, if you give me a function, and if you give me a particular list, I will give you back a particular list.
Basically, if you follow that, if you give an int, I will give you character. If you give me one int, I will give you another one character.
Yes.
I will give you a list of x. I will give you a list of y.
Exactly. That's precisely right. Yeah. Okay. What to do from here? Right. So let's go back to code, and let's talk about things that we didn't talk about. So things that we didn't capture very well at all. So far, I've been really focusing on lists and list transformations. And the reason I've been doing that is because there's a nice story through the monoids. So now we've got like an army of abstractions to help us understand that. But not every program is a list transforming program. I don't know if you've tried. There are other things you can do with programs. So let's try to see what other data types we might work with. So far we focus on lists. What other things could we have in our programs? Well, we could have things like integers, we could have trees of things, we could have maybe values, all sorts of other things that we could have. So far I've talked about this. Can we apply our theory to all of these things as well? Thankfully, with some modification, yes. So to do that, so in terms of where we're heading, I'm going to decompose lists in terms of how they're defined as an inductive data type. Then I'm going to decompose these guys as inductive data types. And I'm going to show that the tricks we can apply on lists apply to these things as well. And that means that programs that act on integers will have a kind of a map reduce equivalent as well. Things that operate on trees will have a map reduce as well, and so on and so on. So let's try and do that. So, what is a list? I feel like I should have done this hours ago. A list is equal to two things. And just to stop confusion, I'm going to stop writing lists like this. I'm actually going to list A now. So this is the empty list. So this says, here's an element of this thing, it's the empty list. We also have this single colon recognition. So single colon, as Benjamin asked earlier on, what is it? It's the thing that puts a value, A, produces this. So if the first parameter is an A, and the second parameter is a list, we create a list that includes both of these things. Okay. Now, what MapReduce did is it exploited the fact that lists are monoids. And if we didn't know that up front, we might come up with a slightly different recursion scheme that just looks at the data structure itself and exploits that structure and nothing else. We call this particular recursion scheme a fold, and it goes something like this. A fold right, in fact, is a function that given an A to B, the list A is reducing B. Now, you'll see lots of similarities with what we did in MapReduce. There's one fewer argument, and this in some sense does the mapping and the reducing at the same time. The way it's defined, let's define it and then let's use it. So actually, let's use some examples. So the sum example is equal to fold R plus 0, and the prod example is fold R times 1, and the sorting example is equal to fold R insert rather than merge on the empty list, where insert takes a list and inserts the value into its right orderly place. So this is, you see a difference here between MapReduce and this because of the asymmetry involved. So this thing here has type A rather than type B, so we can't quite do the same merging trick earlier on, so we have to do the insertion block instead. So how is this defined? We give it some function f, some continuation k, some value k, and if we have the empty list, we'll get fk, for fk, x is equal to f applied to x, and then the result of fold fk x's. So this is the general pattern, and go into the details and show that these things are equivalent. But what I want to point out is, unlike the MapReduce, where we had to notice that everything was a monoid, here we don't need to notice half as much. This is actually a very, very boring piece of code. I'm going to just rename a few things for you. This thing is called the empty list. This thing is called the cons operator. Okay, so this is called empty, or actually let's call it nil because it's shorter to write, and let's call this cons. Okay, so instead of calling this k, I'm going to call this nil because it's what we want to do in the nil piece. So I'm going to write k, and you're going to write the word nil. Remember, nil doesn't mean the nil list, it means the thing you want to do to the nil list. And f is really the thing that replaces cons. So here's a cons, and we made it an f instead. So I'm going to call this cons. And here, I'm just going to write x cons this thing. So what am I trying to emphasize? I'm trying to emphasize that something extraordinarily boring happens when we form a list. Whenever you have a list of things, like x0, x1, x2, x3, this is equal to x0 constant to x1, constant to x2, constant to x3, constant to the empty list. Okay? What does fold do to this thing? If we fold R with cons, and nil. We're basically going to transform all the conses into conses and the nils into nils. So it's going to be x0 cons, x1 cons, x2 cons, x3 cons, nil. Now, somebody might complain, what on earth is this cons in quotes? It's me being a bit lazy and making a prefix thing become an infix thing. So I could instead write this as cons, 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 x1, x2, x3, x4, and nil. And it with brackets in the right places. It means something. So what I'm trying to stress here is that foldr is just saying, please replace the constructors of your data type with functions instead. Why are we doing this? Because that strategy is going to work for arbitrary inductive data types rather than just lists. We don't need to spot the monoid. We can just immediately say we're replacing like with like. Okay? But we need to do a bit of work before we can actually say something like that sophisticated with this. And thankfully, we have a little toolbox to do that. Yeah.
Is there a parallel story going on with Lisp and Lambda calculus? Yeah. And is there a sort of an analog? Is there two cultures going on here that you could say, you could tell the same story?
Yeah, absolutely. Yeah. So Lisp is really close to this. We could do pretty much all of this in Lisp just fine. The difference is that Lisp is actually untyped. And so when we start doing stuff that requires us to know the type of thing that we're doing in order to provide the right function, we're going to have to start encoding all the types in Lisp, and then essentially end up with a typed Lisp, and then things get a bit hairy. So notationally, it's just going to be very heavy. But if it's erasing the types, it would be the same. Okay. I've not quite convinced you that foldr is very powerful yet. I kind of want to. Okay, who feels like they need to understand foldr a bit better before we could carry on? Actually, what time do I have to start?
45.
Good, nobody wants that. So what I want to talk about is notice the pattern that's going on between here and here. What is the type of cons? And what is the type of nil? Ambiguity intended. So, little cons has type, it's the first parameter is this type, A to B to B. Cons, the constructor for this, has type A to list A to list A. Nil has type B. Nil has type list A. Can you see the pattern yet? So what we're doing is replacing these in lists. That's what we're changing, right? What's special about the word list A in these constructors? Well, they are the thing that we are defining, right? That is the special part of it. So if we can somehow capture that this is the special thing, this is the recursive site of our definition, somehow, then we can get this cons for free from this cons. Right? And then if we can get cons and nil for free from the constructors, that means we can get the fold for free from data type. And that means that we've got the recursion scheme from the data. So we fulfill Tony Hoare's observation from the 70s that says the structure of the computation follows the structure of the data. Right? And so, back to the question, why? Well, we know that this thing here is well defined, and it's well defined whatever the data is well defined. So we know we have terminated programs in all cases. Slight tangent. Something interesting you can do in category theory is reverse all the arrows of your functions. So you can make them go backwards. And that still defines a category as well. It's called the opposite category. And so everything is like in a bizarro backwards world. What happens when you start doing the game you're about to do in the bizarro world is rather than making functions that reduce data, you create functions that produce data. So rather than inductive, you make co-inductive definitions. So rather than things that terminate, you make things that screen. So online screening algorithms all come out of the thing for free just by reversing the errors. But I only have half the time I need. Yeah.
Well, I confirm here you mentioned a lot about category and also the moment. And basically that way what mathematics when you learn the category the field theory, you have the same concept.
Absolutely. Yeah. And so a category is a generalized monoid, in some sense.
So that means you assume everything here and you learn this mathematical background they're in there actually.
I don't know exactly what I've assumed. Forgot to say something quite interesting. When we were talking about monoids, I just want to see if I destroyed enough the board. Yeah, okay, I want to say something. Can you hold that thought? I want to just go back to monoids for something interesting I should have said. Thank you. Your question reminded me about monoids. So the categories we've seen so far have been sets, monoids, categories. And in some sense, they all behave a little bit like sets. And so we're like, oh my goodness, this is so boring. Why is it all exactly the same? Here's a category that's slightly different. A monoid m plus epsilon is a category. Okay, that's really, really weird. What on earth do I mean? So we have a category, I need to talk about the objects, and I need to talk about the arrows. What are the arrows? What are the objects? What is the composition? What is the identity? All interesting questions. So we need to have a set. Now, I would suspect that if I asked for a show of hands and you felt confident and not half very sleepy, which set should we use? Most people will say M here, and you would be wrong, because we don't use that set. What we do is we use the singleton set mob instead. This is a set that includes nothing other than this blob. Okay, it's a set singleton element. I could have written the number 42 here instead. I just need a singleton element.
So that's what the public proposition is for.
No, yeah, I should probably write start.
Okay.
So that is the set that we're going to be dealing with. I also need to give you the definition of category still. Well, I also need to give you some morphisms. So given two objects in this set, we better have a morphism between them. So there's only one object here, it's just star.
Then what is star? I mean, you replace M by star because M is the correct answer for this problem.
Yeah, I'm thinking of, so I'm allowed to do kind of what I want here, right? I'm going to just write a set, and I'm just going to demonstrate something that's a little bit weird. And I'm just choosing, for whatever reason, which will come here later on, this to be a singleton set. I'm allowed to choose any set here so long as it obeys the category laws to make something.
Okay, what is the singleton?
A singleton is a set containing just one thing.
But what is one thing? Is it an integer or a dog?
It could be your cat, it could be a dog, it could be a star, it could be a number, it could be anything at all. So it's a set containing one thing. Like, here are some examples of singleton sets. Right? This is a set containing one element. This is a set containing, I don't know, a different element. This is a set containing something which is a star. I don't even know what a star is. These are all, in some sense, equivalent. They all just contain one thing. So they're very boring in that sense.
Okay, so it's only an object of type anything.
Who cares? It's just a thing. Yeah. So this thing is just a single set containing just one single thing. Yeah. It has no properties. Like it really could be anything at all. So I've just written star. It's totally arbitrary. So now I need to write the hom set, which means the set of arrows from all the objects to the other objects. There's only one object here. So it's the hom from star the star. This thing needs to be a set. I need to provide a set for this, right? Which set should I make it? Well, I'm going to make it the set M. This is utterly bizarre, right? So think of the monoid. The favorite monoid is going to be this one. And what I am saying is that the number 1 is an arrow from star to star. And I am saying the number 42 is an arrow from star to star. It's not element like it used to. This is a really weird world I know. I'm telling you that numbers are arrows. Okay? And I need to have an identity function that goes from star to star for the identity. And I need to have a way of composing these star-to-star things together in a way that makes sense. Right? So given some x and some y in M, which of course means that x has type star to star, and y has type star to star, I need to produce a new thing in M, which will also be a star to star thing. That's going to be the composition of x dot y, right? How do I compose these things together? How do I compose a number with another number? With the O plus, right? With the operation on the void. Okay, and this is a valid arrow from, from the star as well. So this is like an utterly bizarre example, and the confusion is multiple because we've got a singleton set, we've got numbers aren't numbers anymore, numbers are arrows, and I've got composition of things. What's the identity? It's your favorite number, 0 or 1, 0 in this case, right? So this would be the epsilon is the identity. Right? And this will behave nicely with regard to everything else. Lots of questions, yeah.
If you have two monoids as categories,
Yes.
the functors between them
Yes.
will be the monoid homomorphism.
That's exactly where I was heading. Well done.
Sorry.
Yeah, that's exactly right. Yeah, so that's a very good observation. So what I've gotten to and is this interesting statement that monoids are categories. A functor from one monoid to another needs to observe 2 laws. It preserves the identity and it preserves the composition. The identity is epsilon and the composition is plus. But oh my goodness, epsilon gets preserved and plus gets preserved. This is the functor law. So a monoid homomorphism is just a functor from a monoid to another monoid. So that was the interesting thing that I wanted to do. Just as it's a show off that the theory is actually quite deep, and it shows the connections between stuff that is well related in a very fundamental way. Because when we start to talk about monoid homomorphisms, we thought, well, it kind of makes sense, right? This structure is all being preserved. And I made some claim about Capstan theories about structure and preserving structure. And functors turned out to exactly tell you what monoid homomorphisms are directly. Yeah, there was another question, I think. Is it you?
I was just for the sake of it, like, can you produce like this category with like a set with 2 elements, or can you only do it in this way?
That's the bit like what Isaiah was asking later on. Yes, but we need to do some versioning to make things a bit more equal, and then so much approach these things with. Yeah, I think so. But yeah. Any other questions? Okay, so that was just an interesting observation. The structure of monoids, functors, monoid homomorphisms.
Could you say that from what would be go wrong from the set of the M? So you would not.
It would be highly misleading. So I could indeed, if I wrote M here, then here the hom set has a lot more structure in it. So in this particular version, remember the hom says that if x and y are in the object space, then the hom x, y is a set. So if I have M here, this object space is large, it's got all the numbers in it. So now we need to tell you what between HOM 1 and 2 is, HOM 3 and 4 is, etc. So now I've got the whole space of HOM morphisms to fill up. And all these arrows then don't necessarily compose. Like the arrow from 1 to 2 composes with the arrow from 2 to 3, but not with whatever. And I don't even know which arrow you mean here anymore. So it's like we might be able to make some stuff out of this. I think we probably can. In fact, I know we can because we can pre-order on it. And this is related to somebody else. Like, are lattices related to categories? Lattices are categories. This is actually what we'll be doing. But that's actually a completely different structure. It's not. Yeah.
Like you could construct them.
It's a different category, but you could construct it.
Yes. What's just that is business? It was mentioned only once, but is it, let's say, a further abstraction?
Yeah, let's talk about that at break time. So,
Because you have, let's say, categories, right? If you put them like an hour ago or so,
Yeah.
and then you put categories of categories,
Yeah.
and then someone throw in the word lattice, so let's say God mode or
it's not God mode. Category theory is God mode. Lattices are an example of a category. And if you don't know what lattice is, think like an ordering structure. That's just another example of categories. But we'll talk about that later.
is there like a similar data structure parallel to categories playing in the same that has the same inheritance relation?
We'll talk about that later. So I want to finally make time. Yeah. Yes.
Surely it would matter what you choose the star set to be, right? Because like it can't be anything because like we have to have functions on that set, right? So for example, if you chose the star to just be like a singleton set, then the function can only be an identity.
Exactly.
But then you want your function to compose like they do in the monoid.
That's right.
So you can't choose the star to be anything.
Let's try again. So it's any singleton set to do, because notice that what I'm making is the HOM set from star to star. Because there's only one element star in this set, there's only one HOM set to worry about. It's this one. If you chose your rabbit here, then the HOM for rabbit to rabbit would be exactly M.
But like the set of functions from one rabbit to rabbit depends on what rabbit is.
There's nothing here that depends on what star it is.
Because you chose for the home set. Because you chose a subset of what? Well,
Because I told you that HOM star star is M. But that M had nothing to do with star. So nothing on the right hand side of a star depends on the star. It's really just any single set whatsoever.
surely I could make a very stupid choice for star. That would make it not possible for home set of star to be M.
Okay, let's talk about that at the break. So
What if you chose the singleton set to be the set containing M?
that'd be fine.
Yeah. Then you get one of M equals M.
Yeah.
Yeah.
Yeah. And you'd be a bit confused as to what M is doing. It's doing nothing.
Yeah.
But it'd be fine. Yeah.
So, what does a number being, like, if you did choose, if we were looking at a monoid that's natural numbers plus 0, and we chose starting 3,
Yeah.
then what does a 0 being, or 42 being a function from 3 to 3 mean?
Just as much as 42 being a function from star to star means. So the star part really computes nothing other than making the arrows compose, because they have to intersect on the source and the target of the arrow. And they're intersecting on the star. They could intersect on the 42, on your rabbit, on a banana, it doesn't really matter what it is, so long as you're intersecting on something that's fine.
Okay.
So now I make the controversial observation, so this is one instance category being equals nothing. Because you've just taken a perfectly good model, you created some pattern and have quite zero intuition.
Yeah. Yeah,
What's the point?
Well, the point I wanted to make was literally this. Morphisms are functions between monoids. But I can't make that statement until I convince you that a category is a monoid. And unfortunately, the construction of that requires something a bit weird. Yeah. So maybe I should look up on this round more.
Yeah, just
It's been an interesting round of things.
I guess I think maybe the confusion is the sort of weirdness there is that the data is not really contained in in the objects here, right? It's contained in the morphisms themselves. So I guess our intuition for functions is kind of getting in the way because if you have an in-house flow function, right, you have a unit to unit function, right? They're all going to be the same, but we can't like distinguish them.
Yeah.
Like what foo takes a unit, returns a unit, and bar takes a unit, returns a unit. We can't distinguish between those. But here in this category theory sort of setting, we can be more general and we can say like, you know, this foo is different to this bar because of that composition. Like we could sort of propose how.
Yeah.
Yeah. That's
So it's a really useful observation. And I think the thing that my student position warned me against doing this example when I told them I was going to say, oh, it's going to confuse everybody. You're absolutely right. But the reason I like it is precisely because of the confusion it creates. So it makes us reevaluate what we think arrows are. Because up till now, arrows, they're easy. They're just like function-like things, right? This is totally not a function-like thing. This is a really bizarre construction that tells you that numbers are arrows. And you're like, surely you said that wrong, Nick. You didn't mean that numbers are arrows. Numbers are particular things. They don't apply to each other. But they jolly well do apply to each other because of moral proposition, right? So it does bring up lots of interesting questions. And so even if I've sacrificed the actual punchline of this lecture, I think it was kind of worth it. So I think, is it 5:30 till we finish?
Like I said, we've got 12:45.
Okay. So should I speedrun the last part?
How long do you need for a punchline?
Sorry?
How long do you need for a punchline?
I'll speedrun it. So I'm expecting permission to. Yeah. I'm going to be brutal now.
You have the lunch break.
Yeah. So I'm going to be a bit brutal. I'm sorry if you don't keep up. So. What do I want to say? What I want to say is this construction of lists is kind of we want to abstract what a list is. So before I abstract, I just want to remove some of the inessential details. I'm going to work with lists of integers, not lists of arbitrary types, because the type A is just going to confuse us. So I'm just going to pretend that this is an int list, like this, because that will simplify the story later on. Okay, and so this is no longer an A, this is an int, and then these are numbers, and then here we go. Okay, it's my list. So the thing that we want to abstract is the recursive call to the list itself. Okay, and the way that we abstract over a type is by using a functor, which is why I just erased all the A's so you don't get confused about which functor I'm talking about. So I'm going to define a new functor. I'll do it in Haskell. And I'm going to call it not list. I'm going to call it, I could call it list K, or I could call it list F, or I could call it list with an underline underneath. Okay? It's just a different thing. It is not the same as list. It's got an underline on it. So it's a different identifier. But I'm not wanting to reinvent names, so I'm going to underline it. So this, okay, and this is a functor in position K, where we have something called the nil constructor, which has type K, and we have something called the const constructor, which has type int to K to K. So what on earth am I doing here? If you compare this to this, it's exactly the same definition, except that here, instead of writing the recursive thing IList, I'm writing the thing K instead. So everywhere where it says IList in the definition, I'm using K instead here. This is exactly allowing me to abstract the position of this component here, which is exactly the ingredient I need to pull away from lists particularly. So list is not to list unbar. However, I'm going to introduce the fixed point of things. So really from fix. Fix is something that if you give me an f that is equal to there's one constructor, and if you give me f of fix f, it'll come back fix f. So we start going into domain theory a little bit. The idea with this is a data type that creates recursive data types. So you give it a functor f, like list underscore, and it will produce for you a recursive data type that does the recursion at this point k that we had over here. So in particular, the type of lists is equal to new lists. So modulo constructors. So here we've got an in constructor that gets in the way. So let me just give you a few examples just for some intuitions.
I think we recorded data or we covered arrow.
Data type.
Not arrow.
Not arrow type, data type. So let's make things of type new list. In order to construct something of this type, okay, I've written new. I don't want to put I'm going to write new instead. So in order to make something of type new f, I need to use the in constructor. So in, and now we need to make something like f new f to make it work. What is f? F is list on the bar. So then I can use the in, for instance, as a this is the empty list. If I want the list with one element in it, I can do in. It's enabled, I can choose cons. So cons 1, for instance. But in this position, I need to put a k thing, where k is instantiated to new f, which means I need to make another new f here. This has to be something like new list. What can I choose? Well, I can choose this thing. So in here. That's the list containing the element 1 followed by the empty list. And if I want to do number 2, do something like this, and so on and so on and so on. So I have a recursive data type now, but what I've gained is the ability to talk about this k parameter here instead. So functions of the form list k to k are going to be quite useful. They're going to be things that say, if you replaced the recursive position with the solution I wanted, I could give you back the value that you need. So, for instance, list int to int. Let's call this, these things are called algebras. I'm just going to write alpha for algebra. Let's write a function of this type, just to see what it does for us. It has to operate on something like list under. The list under is something like nil. And I need to give you back an integer. Let's use our favorite monoid. Then x. Now x here has type int. And y here has type int, because k is also int. So what can I do with my two ints? I can put them together, right? So this works just fine. You'll notice that this looks like all the information we needed for the fold. It is all the information we need. So I will stop for this equation. A fold basically says if you give me an algebra of this form, then I'm able to completely destroy any data of this type. So what this fold says, if you give me a list k, then I can do a reduction like this. And the nice thing about this definition is, I won't have time to go into it. Nothing about this definition will actually involve the list constructor per se. All of it will just be relying on the fact that this is a fold. So we would say that the more general form is what we call a capital morphism, which means a destroying morphism, is something that says, if you give me any functor f at all, as long as it's a functor, in this way. Now, as a parting thought, this thing is going to be like the general map reduce, and I've generalized it away from this as an arbitrary path. It turns out that natural numbers have an underlying structure class. So the natural numbers are either 0 or the successor of something. So this pattern also works on natural numbers. If you tell me what to do on the 0 case and in the successor case, I can destroy the natural numbers. And we can play the same games with trees and with basically polynomials and any other data structure that's composed of lots of different things, and end up with a catamorphism that crushes it all out. So this is the punchline that we didn't quite get to, but hopefully it's giving you a flavor for where this sort of direction of research goes into. We're trying to generalize away from not just maps and reduces or folds, but folds over arbitrary space types. But with that, go get some food. Thanks.